Let's see if we can get this screen shared. There we go. All right, you guys should be seeing what I'm seeing.
I see it.
Dismiss. Perfect. I've got a little bit of a lag. I'm going to let it kind of time out here. Dismiss. There we go. All right, perfect. So if you'll remember, fellas, what we did last week was we started dealing with formulas, right? We talked actually quite a bit on Friday about manipulating formulas. And we had said that, it's just a matter of using inverse operations. We had a volume formula for a cone, I believe. We talked about degrees in temperature, and then we looked at the area problem with a trapezoid. Today we're going to continue on with some more examples, okay? And I had given you guys some homework over the weekend through deltamath.com, and we'll talk a little bit about that here in just a bit. But when we look at an equation like this, the first thing we want to do is we want to figure out what is it that we're trying to isolate. What is it we're trying to get by itself? And in this example, y'all write down example 4 for me in your notes. We got s equals 2 pi r squared plus 2 pi r h. It says solve for h. Okay, so we want to identify where that variable is in our formula, and we want to again kind of treat it like I've said before. Shrek is an ogre, and ogre, much like onions, have layers. This equation has layers, and we want to go from the outside and work our way in. Okay, so first things first, you got a couple of terms. You've got an h term, and you've got a non-h term. Okay, so we want to start by moving the non-h term over to the other side. So let's do that. Let's say minus 2 pi r squared from the right side so that it cancels out. And on the right side now, we're just left with 2 pi r h. And whatever I do on the right, I have to do on the left. So I've got now the left was s. Now it's s minus 2 pi r squared. All right. And then again, I'm trying to get h by itself. And so when I do that, you know what, I'm gonna be calling on people. I've got what y'all might have heard my little printer going during prayer just now. What I've got is I've got my roster printed out, and each day I'm gonna try and call on each of y'all. So when I call on you, if you can unmute your mic and give me an answer, that'd be great. We'll start with Tiago. What about getting h by itself now? What should I do to both sides to finish isolating h? What do you think, Tiago? Tiago, I hear you. Go ahead and talk, buddy.
Divide by 2 pi r.
Very good. I like how Tiago said, just get rid of it all in one fell swoop. Could we just divide both sides by 2? Sure. And then pi? Sure. And then r? Absolutely. But if we want to be efficient about it, do just like what he said, suggested there, divide both sides by 2 pi r, and let's get rid of all 3 of those factors all at once. He chose division because that's the inverse operation of multiplying, right? So we got h by itself now, and then over on the left, we got the whole left-hand side divided by 2 pi r. Now there is another way of expressing that, like if instead of dividing the whole left-hand side by 2 pi r, if we had wanted to, we could have, let's see here. Copy this, and we'll kick this over here. All right, so if we had wanted to at this point, instead of dividing the whole left side by 2 pi r, if we had wanted to divide each individual term by 2 pi r, right? Whatever I do to the right side, I got to do to the left. I got to do everything on the left. So I could, as I showed over here in the box, we could do the whole side by 2 pi r, or we could do it over here. And what's interesting here is that the 2 cancels out, the pi cancels out, and the r, there shouldn't be an r squared on the bottom. Sorry about that. The r on the bottom cancels with one of the r's on top. So that would leave you with s over 2 pi r minus r. And that's an alternate way of looking at your answer. Not that I have one preference over the other, right? They're both getting h by itself. But just like imagine you're taking like a multiple choice test or something like that, and maybe this isn't one of the options, but this is, right? We want to be versatile. We want to be able to recognize that, oh, what they did was they split it up and they said, hey, let's divide both of those left side terms by 2 pi r and see what shakes out. Okay. So questions on example 4? Go for it, Lewis.
How did you get like the negative 2 pi r squared at the very top? Like, what did you do to?
Great question. So if you look back at the beginning, what we had said was we had a non-h term over here. This was a term that did not have h in it. Okay, that's that outer layer of the onion that we want to take care of first. So what we said was that they were being they were rather those two terms, this term and this term, they were being added together, right? So to undo that addition, what we said was let's subtract both sides, say 2 pi r squared minus from both sides, minus that. So whatever we do on the right to cancel that non-h term out, we do on the left as well, 2 pi r squared. And some teachers will describe it this way, Lewis, they'll say, hey, quote, move that term over to the other side. And I've heard teachers before say, if you want to change sides, change signs. So like it was positive 2 pi r squared, and so therefore on the left it should be negative 2 pi r squared. And that's where that negative term right there came from. Good question. Anybody else on example 4? Nope. All right, let's roll right on into example 5 then. This one says the area of a triangular painting. And let's see here. Paul, what do you think I should do? I didn't even read the whole first sentence, and I've got in mind something that I need to put together. What should I do?
The formula for a triangle is area is base times height times 1/2, right?
This is true.
Okay.
What shape did you say?
Triangle.
Okay, so I might, and you guys, y'all are still kind of learning how I like to operate at this type of thing, but one of the things y'all will learn about me pretty quickly is that I'm a picture person. If I can see the problem, if I can visualize what's going on, man, I'm solid. So I'm going to draw a picture, okay? And so Paul's absolutely right. And Paul, you can mute yourself again, bud. All right. So Paul's absolutely right that we, in sort of our prior knowledge, we've got this notion of the area formula for a triangle involves base and height, right? So area equals 1/2 base times height. So all three of those things in the back of my mind should come onto my paper somehow or another. So it says the area of a painting is 126 square inches. So that's going to be the A value. Okay. It says the base is 18. So that's the B value. And we said, what is the height? So that's what we want to get by itself. Now, there's two ways you could do this one, fellas. You could go ahead and plug those values in initially, or you could go ahead and solve for H initially. And actually, I'm going to take the second tack just as an exercise. I probably wouldn't do it that way if it was me. But let's go ahead and get A equals 1/2 BH to where H is solved for. All right. So we got A on the left. We got 1/2 BH over there on the right. Reed Johnston, what should I do to both sides to get H by itself? And you could either take 2 steps or you could do it all at once.
Multiply. Wait.
I liked what you said. You said multiply. Multiply both sides by what?
2/1.
Yeah, very good. And that's what was that R word, Quentin? That 1/2 and 2/1. You remember what that R word is? Quentin, what do you think? We had 1/2, and we flipped it, and that's 2/1. It's an R word. What's it called again?
reverse.
Not the reverse. Nathan, what do you think? What do you think, Nate?
Reciprocal.
Yeah, very good. Reciprocal. Okay. So when we talk about getting rid of a fractional coefficient, that's exactly what we want to do. We want to multiply by the reciprocal. That's just a simple matter of saying, hey, let's multiply both sides by 2. We say whatever, 2 on the right, 2 on the left. So now we got 2a equals b times h. And Quentin, I'm going to throw it back to you, a little redemption question here, bro. What do you want to do to both sides now to get h by itself?
Divide by b.
Very good. That a boy. So because they're being multiplied, we choose the inverse operation of multiplication, which is division. We're going to divide both sides by b. Cancels out. We got h equals 2a over b. All right, very nice. So as an exercise, okay, I've led you guys through that. What we just did was we solved for h. Now let's actually put it into practical purposes here in the actual problem. Okay, what did the problem say? The problem said 126 is the area, right? 18 is the base, and we want to know what the height is. Now, in that case, in orange there, look at what we're doing. We're just plugging and chugging, aren't we? Okay, so half times 18 is 9. And then if I've got 126 on the left and 9h on the right, just like Quentin said a moment ago, all I have to do is divide both sides by 9, right? So I got h equals, what's 129 divided by 9? I know it is multiple of 3. I don't know if it dump. Why did I write 129? I think I was saying the word 9 and I wrote the word 9. Y'all ever do that? Where you're saying what you where you write what you're actually saying instead of what you're supposed to. 126 is a multiple of 9, so what do we get?
14.
14. Does anybody concur with that?
Yes.
All right, not too shabby. And again, we could have used over here in green, we could have used the same tactic. We could have said 2 times 126 divided by that base of 18, and that would have gotten our answer as well. Okay, the nice thing is that if you go ahead and solve for h like we did in green over on the right hand side, then you can solve that unknown if it's several different scenarios. So like instead of having to do the orange computations over and over and over again, like if we were running different iterations of the formula and the values, if you go ahead and solve for h, then you can just plug it in whatever you want to and not have to worry about the algebra each and every time. Here's an example for you guys. Okay, this is example 6 right here. It says the measure of one angle of a right triangle, bear in mind we're going to talk about right triangle, is 40 degrees more than the measure of the smallest angle. Find the measure of all 3 angles. So you guys try that one out. And again, I would encourage you, make a drawing at this point. Make a drawing and then see how you do. I'm going to fill up my cup with some water and then we'll discuss. All right. Hey, let me ask a nosy question while you guys are working. You know, I know Christian Brothers is shutting its doors for 2 weeks. Are you guys still going to y'all's middle schools like you would normally do?
Yes.
Good.
Yeah.
Good. And so like when we end our class at like 10 till, do you guys just like hop in the car and skedaddle on down the road?
Yes.
Gotcha. All right. So let's see here. I've got my list of people that are on the call. I'm really trying not to call on somebody that's not here. Alex, I'm gonna call on you since I see you're in on the call. Alex, when it says right triangle, tell me what you know about that. What does that mean? Mr. Went.
means the triangle has a right angle.
All right, what does that mean when you say right angle?
A straight line up and down. Right.
All right, a straight line up and down. So I got that. I got one of those drawn. What else? Can you tell me a number that means?
90 degrees.
There you go. Good. Your mic is a little bit soft spoken, so I had to try and strain to hear you, and that's good. So 90 degrees, and this is kind of a lousy triangle picture that I've drawn here, but you guys get the idea. So prior knowledge wise, a right triangle means that one of the angles is 90 degrees, okay? And that's real basic knowledge. I mean, you probably learned that back in 6th grade, maybe even, okay? So when we look at the rest of the information here, it says one of the angles, pardon me, one of the angles is 40 degrees more than the measure of the smallest angle. So like the way I've drawn my triangle, this might be different from how you've drawn it, whatever. We might have 30 different drawings in a classroom, right? But look at what the smallest angle, for me, the smallest angle is the bottom right-hand corner. So if I let that be X, Joey, how could I represent the other angle in terms of X using this notion of 40 degrees more than the measure of the smallest angle? What do you think? Joey, what do you think, buddy?
I'm not really sure.
Okay, think about your age right here. What's your age, by the way? How old are you?
14.
Okay, what would 40 more than your age be?
54.
Perfect. How'd you get that?
Added 40.
Okay, so if this angle is X and I want 40 more than that, what are you going to do to it?
Add 40.
Add 40. Very good. So this angle, fellas, is X plus 40. Very good, Joey. And so the notion here is that if we're given, and what I'm kind of trying to do is work through our 5-step word problem solving method, right? To where we figure out what they're asking. They want all 3 angles. We assign a variable. I don't know if you guys caught that, but what I did was I said, hey, let the smallest angle be X. Okay. And this is a kind of a rule of thumb. I'll actually take time to type this in for you guys just so that you can make sure you have it in your notes. I'll have to probably shrink my font size down just a little bit here. It's often a good idea to let your variable stand for the smallest unknown. All right. And the reason I say that is so that we can use that operator that Joey just told me to use, so that we could use, addition as opposed to subtraction. Not that we're scared of subtraction, right? But when we add, oftentimes things stay positive. When we make fewer mistakes, I've found that is the case with me. So I've said let X be my smallest angle, and then we did X plus 40, right? Joe Edwards, what if we had let X be, like what if I had said, I want X to be my bigger of the 2 angles. How would I have to express that smaller angle then?
Subtraction.
Yeah, we would have to say X minus 40. And not that there's anything wrong with using subtraction, but again, I've found that I make fewer mistakes when I keep things positive. So just word to the wise, fellas, okay? Now, back in blue here, the way we've got this worked out. Step 3, we've said, is the hardest step, isn't it? Okay. Step 3, we've said, is the most challenging step because that's writing an equation. And let's see if, I don't know, Jack McBee, you want to take care of that for us? What equation could we come up with? It's an open-ended question, I know. What do you think, Jack?
Maybe x plus 40 plus 90 equals 180.
Holy cow, dude, you hit it out of the park. Well done. Where did you get that equation, if you don't mind asking? Like, what prior knowledge did you bring to the table knowing that would help you in this problem?
A triangle has 180 degrees, and we already have 90 degrees.
Perfect, dude. Absolutely perfect. Hey, let's all make sure we understood that as well. That's some good prior knowledge from earlier, like I said, late elementary school, early middle school math, that the triangle, the sum of the interior angles of a triangle add up to 180. So if I took all three of my angles, they should all sum up to 180. And then boom, we've got our equation. Now we've got an expression for all three angles. We add those three expressions up, set it equal to 180. Notice they didn't tell you that in the problem. They didn't come out and say, hey, dingbats, add all three angles up and set it equal to 180. They expected us to know that, didn't they? They expected us to know that. All right, John Zweig, simplify the left-hand side for me, please.
Subtract 90 from both sides.
Before you subtract 90, I want you to combine like terms on that left-hand side, please.
You can combine 40 and 90 to 130.
Good. What else can you combine?
X and X to 2X.
Perfect. So now we got a two-step process to solve for the X variable there. And Lewis Thomas, go ahead and tell us what to do there.
You can divide by 2.
Okay. Now let me pause you real quick. That is totally legit, and you could definitely divide everything by 2 right now. We would get X plus 65 equals 90. I have no problem with that. However, as a course of like best practice, Lewis, let's move that 130. Let's get that, you know how I sometimes will talk about a dog and a cat on the side of a fence? All right, so like if you pretended like here's a dog, whoops. Here's a dog, here's a cat, and here's another cat, right? In other words, we've got 2 cats that want to get together on the same side. So why don't we, instead of dividing everything by 2, which again is fine in this case, but maybe less preferable in other cases, why don't we subtract 130 from both sides first?
Okay.
All right, so we get 50, and then we can divide by 2, and we get 25. And the reason I say that, fellas, is because at this step right here, you won't always have all 3 of those terms that are divisible by the X coefficient. Okay, you won't always have them divisible by the X coefficient. So Luke, if we've got X equals 25, what do I do to wrap this problem up? Sublet, you with us?
Yeah, I don't really know.
Okay, so check this out. Look at the drawing here. This is where the drawing, by the way, it's a good point to bring up. This is where the drawing really comes in handy, fellas. So like right now, I know what X is. I know that X is 25. And in fact, on my drawing, I sometimes like to label my answers on my drawing. So 25 degrees. I know that it's a right triangle. So I know this one's 90 degrees. So my last thing to answer this question, they said, hey, find all 3 angles. So Luke, what's my last angle going to be if it's X plus 40?
65.
Yeah, very good. How'd you get that?
40 plus 25.
That's all it took, right? So we just took our answer 25 and we said, oh, we can plug it in. And then another check is to go back and think kind of like what, actually I forget who it was at the beginning that told me this, but you could just double check to make sure everything added up to 90 as well, right? So we got all 3 of our angles and we labeled them on the triangle, and that's perfect. And that's a good example for us to sort of apply a little bit of some geometry here in an algebra context. You guys will do quite a bit of that next year. This is a typical geometry question, standard level geometry question for a 9th or 10th grader to complete. Y'all have any questions about it before we move on to our next one? All right, let's try and get one more in. And in this question, it's requiring a little bit of some background knowledge. Okay, so what I have to do for you guys is introduce this notion of the Pythagorean theorem. And actually, I'm going to make you do it. Who do I want to pick on? Mossy, can I pick on you a little bit? When it says Pythagorean theorem, you got any ideas what that means?
No, sir.
I've never heard of that before. What about you, Jake Oxley? I wonder if have you ever heard of that?
Yes, sir.
What do you remember about Pythagoras?
I I don't know who Pythagoras is, but I know what the
That's what I meant. That's what I meant.
a squared plus b squared equals c squared.
Okay, so I don't see A, B, and C on my picture. What translate that to this scenario right here?
So the smallest two sides, which are a and b, those sides length squared equals the longest side squared.
All right. So what we want to do, that's very good, Jake. What we want to do is we want to get a little terminology out of the way. Okay, so the Pythagorean theorem is an if-then statement. All right, if-then means it runs in one direction. You've got a hypothesis. So if ... that's my hypothesis. And then I got a conclusion. So it's if ... make your hypothesis, then ... you've got your conclusion. For instance, if Clyde is a pelican ... then Clyde eats fish. Okay? So my hypothesis was, hey, Clyde is a pelican. Now, are all Clyde's pelicans? No. Okay, so like my grandfather's name is Clyde. So you know, if Clyde, however, is a pelican, then I can follow that up by saying, oh, okay, well, I know what I can conclude about Clyde. Then he eats fish. All right. So what our hypothesis is for Pythagoras is that if we have a right triangle, and in the last example, I'm still not happy with my right triangle. In the last example, we talked about how we had a 90-degree angle. So that's the hypothesis of the Pythagorean theorem. If we have a right triangle, all right, now check this out. When Jake was discussing like the quote smaller sides, what he was referring to was these are called the legs. Whoops. Okay, so the legs are the two sides that emanate from the right angle. So these are our quote legs. Again, that's a vocab word that you guys will see in geometry. And then the side that's across from the 90-degree angle, right? The side that's across from the 90-degree angle, we call the hypotenuse. All right, that's called the hypotenuse. That's the biggest side of a right triangle. And you guys might have heard those words before. Okay. Now, typically what we do is we give letters. You heard Jake use some letters. He used A, B, and C. Typically what we do is we name the legs A and B. And typically what we do is we name the hypotenuse C. Okay, that's very typical. That's standard operating procedure. It's not, you know, you don't have to do it that way. We could do X, Y, Z, R, S, T, L, N, E, whatever. Doesn't matter. But the notion is that Pythagoras says if you have a right triangle, then the sum of the square of the legs equals the square of the hypotenuse. In other words, A squared plus B squared equals C squared. Okay, so our hypothesis was if we have a right triangle whose legs are A and B and whose hypotenuse is C, our conclusion, then we know that A squared plus B squared equals C squared. Okay, so what we do then is we come back to a problem like this. This is a very basic Pythagorean theorem question. We come back to a problem like this and we say, oh, I've got a right triangle. What are the legs? They're X and 12. What's the hypotenuse? It's 13. Okay, then I should be able to, step 3 of my word problem solving method, right? I should be able to write an equation. X squared plus 12 squared equals 13 squared. Okay, and that's my equation that I would solve in this kind of scenario. Now we know what 12 squared is. That's 144. Do we remember what 13 squared is?
69.
169. And then look at that. It's a two-step problem from there. We subtract 144. So we got x squared equals 25. And then we take the square root of both sides. I'm out of room here on my screen. Hold on. That's a little bit better. We would take the square root of both sides. And what would y'all tell me? X equals Anyone?
5.
5.
Yeah, x equals 5. And so what we do is when we answer this question, we find the other leg. We found that x equaled 5. And actually what this constitutes is this constitutes a Pythagorean triple. And we'll have to start with that notion next time we meet tomorrow morning. We'll start talking about Pythagorean triples. This is a real typical example, again, of where you've got a sort of a set of prior knowledge that you have to bring to the table. In this case, being the Pythagorean Theorem. Pythagorean Theorem is a big, fat, hairy deal. We're going to talk about it a lot this year. You guys will discuss it a lot next year as well. So if you have any questions in the meantime, hit me up and I'll try and help you guys out. Great job today, fellas. Thank you for logging in, and I'll see you tomorrow. Let Jesus in our hearts.
Forever.
Forever.
All right, fellas. Y'all have a wonderful day. Thank you.